Okay, great. I'm sorry for that. Hi, I'm from. I will never use it. Okay. Hi, I'm Takeshi from University of Massachusetts Amherst, and today I'll be talking about this topic. And this work is done with Mike Lanighan. He's here, and Professor Grupen. So, planning and executing tasks in partially observable systems is a challenging problem. You know, robotics has a lot of uncertainties from perception and action. And a common approach to plan and execute tasks in robotics uses task and motion planners. And in the task and motion planners, high-level planners rely on symbolic representations of the problem that makes planning tractable. The question is, where did the symbol come from? Or can you rely on those symbols? And the grounding symbols representation in actions and experiences have been investigated by many researchers. But in this project, we are interested in when and how to symbolize objects. So this is a more computer vision problem. And some objects are ambiguous from a single view. So even if you use state-of-the-art deep learning technique, it may fail from the single image or a single point of view. The good thing about the robot is the robot can take multiple actions to gain more information about the object to resolve these disambiguities. And we have proposed a belief space planning approach to solve these problems in the previous work. And as you know, it is hard to abstract uncertainty in a symbolic world. On the other hand, belief space planner can work well with uncertainty if your task is something like computer vision problem, like estimate pose or recognize the object. However, if the robot needs to do some high-level task, the belief space planner will have some computational issues. On the other hand, symbolic planner can plan efficiently in a logic-based world. So we like to use these advantages to solve the problems with uncertainty in robotics. So in this work, we introduced a hybrid planner that actively controls uncertainty and yield robust state estimate with bounds on uncertainty that can make effective use of the powerful symbolic planning techniques. So in our framework, symbolic planner handles task-level constraints, and the belief space planners overcome uncertainty in low-level interactions with objects in the environment and ground symbols. And then we demonstrate our approach in a low-level by constructing physical copies of simple structures like this. So this is abstract version of our framework, and then please look at the pseudocode in our paper in detail. So the robot is given a subtask from the task planning layer. For example, the robot needs to find some object given the task. For example, if you need to find an object, it involves with a lot of uncertainties from perception and actions. So belief space planner layers try to solve the issues. Belief space planner layer provides an action that minimizes the uncertainty. And given the action, the robot performs the action and observes the outcome of the actions and update the beliefs. The important thing is the robot iterates this process until the robot has the confidence about the object. Once the robot has the confidence on the object, it's time to symbolize the object. Now, because the symbol is very reliable, because the robot actively condenses the belief on the object, we don't need to worry about uncertainty about the symbols at the task level. To model object, we used aspect transition graph. Aspect transition graph has aspect nodes that represent features from the certain camera views. And edges represent some action. For example, if the robot looks at 254 right now, and then if robot applies some action 1, robot is most likely to see 4, 5, 6, but all of the actions is stochastic. Sometimes you will see different aspect. And the robot can take multiple actions to manipulate the object. Then we use this aspect transition model as a forward model in the belief space planning. So this is our belief space planners. Our state space in this planner is the aspect node. And in this part is a base filter. So given action and observation, we update the beliefs. And our belief space planner takes information theoretic approach. So that this planner finds an action that minimizes the uncertainty. In our case, we take the action that maximizes the information gain. Because we have the forward model, we can compute the expected entropy. Then we can compute the information gain. And instead of reason action over the original state space, given the task, we partition the state space so that we can minimize the number of actions to condense the beliefs. In this case, for example, the object needs to find an object which has 3. And these aspect node satisfy the subtask. So we partition these objects. In this case, we have 3 object models, and then these 2 object models satisfy the task. So we partition this as a class target, and then the other aspect nodes as class non-target. So we reason action over 2 classes. And if the robot task is to orient 3 on top, means that robot wants to see the specific configuration of an object. In this case, these aspect nodes satisfy the subtask, and then we partition these aspect nodes as class target, and then other aspect nodes as non-class target. Again, in this case also we reason over the action, over these 2 classes. So based on the task, we change the partitions so that we can minimize the number of actions to take. Then once the belief in an aspect is sufficiently high, we can symbolize the aspect for use in the task planning. In our case, we don't need to identify the object. As long as the object satisfies a certain property, we can use it to complete a high-level task. So for example, in this case, we call it hypothesis 0, hypothesis 2, hypothesis 1, and the hypothesis 0 has 1x aspect. And after also the belief exceeds some threshold, we symbolize it like this. So we generate PDD problems at runtime. And any symbolic planner finds a satisfying plan if one is available. If there is no plan, basically the robot keeps investigating area to gain more information about the environment. So for example, this is a PDDL problem. This is a very early stage of the task. So in this case, the PDDL solver cannot provide any solution. However, after the robot interacts with the environment through belief space planner, we keep adding the symbols. So those symbols are pretty reliable because we actively condense the belief. And at this point, the robot provides a solution. Solution consists of subtasks. And a given subtask, our belief space planner figure out how to execute those subtasks. So we demonstrate this hybrid approach in a simple copy task with resource constraint situation using our robot, U-Bot 6. So this robot was built in our lab. And other object models, we use AR cube. We put AR tag on each face of the cubes, but this is partially observable from any single viewpoint. And this is visually or dynamically ambiguous. So we have very similar objects. Each object shares some features. And even though we use AR tags, we always have a few centimeter errors of the position, and then sometimes the robot fails to detect the tag due to the lighting conditions, so everything is uncertain. And then task is this stacking box problem, but the robot needs to place the object with a specific configuration. And in this case, we have 3 materials in the resource area, but 3 of them can be used for the first layer, but only 1 of them can be used for the second layer. And the robot doesn't assume the number of materials are there. The robot doesn't know anything about the resource area. So I'm going to show you the video for this demonstration. First, robot register the goals. From the position of features, it symbolizes the goals in the problem file. Then now robot observe the copying area and they symbolize it. So this is clear flow. We added information to problem file, but at this point the robot cannot find a solution from the symbolic planner. So the robot decided to investigate this area. So he wants to have the object which has 1, and then he also wants to find the object with 3 and 0. And from the first couple of observations, he's sure that every object has 1, but he's still not sure about the object with 3, 0. So he applies multiple actions to find the object with 3, 0. So in this case, even the robot looks at 3, 0. Because of the uncertainty, the robot cannot believe it immediately. So the robot needs to take multiple action to confirm that the object has 3, 0. And then after that, we symbolize that information. And in this case, PDD symbolic planner gives a solution. Means that you need to pick and place that object. In order to figure out how to grasp it, the symbolic brief space planner gives an action or parameters to do that action. And then he places, and then he observes this area again. And then based on this information, he updates the PDDL problem. And the symbolic planner solves the problem again. And then it says that, okay, you need to pick and place the hypothesis too. But in order to place it, you need to orient. So in order to solve the oriented task, we use the B-space planner to figure it out. So we don't have any fixed rule to orient, but basically the robot is always trying to condense the brief to satisfy the task. So sometimes the robot needs to look at the object again to condense the belief so that the robot is sure that it has 3 and 0 and then not complete the task. So in this case, the robot correctly symbolized the object, needed to complete the task while not falsify symbolizing improper object. We did 10 experiments. We got 8 successes, but 2 failures due to the stochastic action outcomes. The plan was correct, but he just failed to place the second object, and then we didn't have any recovery system from that, so we got failures. And then this graph shows that how the belief of the object with 3, 0 aspect changes. In this case, we have 3 aspects, and then this is the first observation. From the first observation, if you take the maximum likelihood observation, robot will symbolize that hypothesis 0 has the 3, 0 aspect. But actually, hypothesis 0, that is red line, it doesn't have a 3, 0. So if you just take the maximum likelihood, the robot would have failed this task. So as a conclusion, we propose a hybrid planning architecture that uses a model-based belief space planner and a symbolic planner. And we demonstrated how a belief space planner stabilizes the semantics of feedback from the environment and then ground symbols or symbolize the objects. And our future work will focus on implementing additional action to recover from the failures. And we will present this work at workshop at RSS next month. Thank you.
One quick question?
I'm not entirely sure I understood the way you synthesize high-level symbols for the PDDL planning. Do you, let's say, extract them from a set of symbols, and the belief planner just, let's say, selects some of them and disregards some others? Or do you create them from scratch? For instance, in the Comidari's paper you mentioned at the beginning of your presentation, what they do is they create BDDL symbols entirely from scratch. The BDDL domain is initially virtually empty.
So we have the domains. We have domains. We have predefined domains.
Okay.
So we just recreate the problems. And then from the our models, we have the set of aspect nodes. So when we create the symbols, for example, so in this case, H0 means the hypothesis number. So robot doesn't know how many objects are there. So if the robot finds 10 objects, we just put numbers, those hypotheses. So hypothesis 0 to hypothesis 10. And then after robot investigated, the robot knows that hypothesis 0 has some feature 1 and X is some word code. So it just means that it has feature 1 and X.
Do I understand correctly that the symbol is already there and the robot, by interacting with the environment, selects what is the highest probability symbol among all the symbols available and possible in the environment? I think yes. I believe you are right. Yeah, select from our object models. Yes, from our object models like this.
Okay, the second speaker again.